Let's start the module 2 where we'll discuss your arbitrage free models, right? We got the flavor of arbitrage free models in the end of the module 1, right, where we studied your holy model. Now we are moving into module 2, which is arbitrage free model, which is the next level in your FRM part 2 after your simple drift model. This module is all about the Vasicek model, right? If you see topic number 2 to topic number 8, it's all about your Vasicek model, one of the foundational arbitrage-free term structure models. Overall, in topic 1, we'll talk about your arbitrage-free models overview. We'll recall, in fact, from the model or module 1, your model must ensure that there is no arbitrage, no free lunches. Holy model already gave us the time dependent drift to fit into the observed yield curve. Now, Vasicek adds your mean reversion, which is closer to your economic reality. In your topic number 2, we'll get into your Vasicek model mean reversion, how we incorporate that mean reversion, if the rates are how the rates are pulled back towards your mean rate over time. Then we moved from topic 3 to 5, where we'll talk about non-recombining trees. So here, the point is that early Vasicek tree versions don't recombine. Your up then down, which we saw in the drift models, is not equal to your down then up. This makes them computationally very heavy. And from the exam perspective, why recombining trees are preferred, because there are fewer nodes, simpler calibration, but when the trees don't recombine, it becomes very difficult. Then you have your topic number 6, where we move into recombining trees, right, where we focus on your more practical for pricing, keeps the mean reversion property while avoiding your explosion of your nodes. Then we move to chapter number or topic number 7, where we look at the rate change, standard deviation, half life. That what is the expected rate change? What is the standard deviation of rate change? What's the half life, etc. Right? We'll give the formula for this, and then lastly we'll discuss about the effectiveness of the model, which we have done for no drift also, constant drift also, and for holy also, right? So overall, very heavily dominated by Vasicek, right? Everything is about Vasicek here. There are 3 versions of Vasicek which we are looking at. We are looking at non-recombining trees. Then we are looking at this recombining tree, and then we look at the rate change, etc. We are looking at that. Okay. From the exam perspective, please be aware that you should be ready to write Vasicek models formula. That's the first thing. That is the expectation out of students. Expect question on your half life, right? This is very important, guys. This is very important. Expect question on mean reversion also, very important. These two are quite important from exam perspective. Understand your limitations, which we discuss, your negative rate, single factor, etc. Okay. All right, guys. So let's try to dig deeper. Your We are moving into your module 2. Module 2 is a version where we not only look at the arbitrage free thing also, but we try to join mean reversion in arbitrage, right? So it's the step from your mathematical models where we saw no drift, then we saw constant drift, then we saw holy model. Now we are moving to your economically realistic models, which is your Vasicek, CIR, and your Halvai. So just to give you an idea, okay. So first stage was the first stage of your art of term structure model. First stage was that we learned about mathematical toy models, right? Put it like, I'm just giving you a simple interpretation, right? Mathematical toy models. We studied about no drift, which was the most simplest. Then we move into constant drift. which was more difficult. Then we moved into holy. Right? These were three things. Now we are moving into economically realistic models, right? Which are your Vasicek, your Cox, Ingersoll Ross, and Halvite. Okay, we'll focus more on this, but I just want to tell you that how the things are moving, right? We are moving into more economically realistic models, right? All right. When you talk about your arbitrage free models, let's understand the overview, right? So in this topic, we carry forward the discussion which we have done before was the arbitrage free models. It's a crucial distinction in your FRM between two different approaches to model the term structure of interest rate. Okay, so there is arbitrage free models and your equilibrium models, right? Arbitrage free models are those models which are calibrated to exactly fit your observable data, right? So when you talk about observable market prices, what does it mean? Your treasury yields, right? Treasury yields, right? Your swap curve, right? Swap curve. Why do we do it? Because we want to ensure no arbitrage opportunities, means you cannot construct a risk-free portfolio and profit from that. Used especially for pricing illiquid securities, right? Illiquid securities, your custom securities, your derivations or your derivatives, which are, you know, very complex. Example of your arbitrage-free models, which are those? Holy is this. Vasicek is one. Halvite is one. Right? HW is Halvite. Right? These are your arbitrage-free models. What are the limitations of arbitrage-free models? That the calibration which we are talking about, calibration depends on your assumptions, right? The parallel shift assumptions, right? What you assume depends on that, right? It is sensitive to market data, relies on accurate market pricing. If you don't have the accurate market pricing, it can be distorted by temporary external shocks. Let's say during a crisis, the model calibration can give you misleading outputs. So these two are very important from the exam perspective. There is a small discussion on equilibrium model also, which is not that much discussed in your syllabus, but the point here in equilibrium model is that in equilibrium model you don't force a match, and you don't force a match to today's yield, right? Instead, you derive rates from your economic assumptions. Okay, what are the economic assumption? Means inflation, means consumption, means preferences, right? So it is good for your relative valuation, right? Good for relative valuation, right? So let's say if the market prices are kind of distorted, in that case the equilibrium models will hold perfectly well, right? But in that case arbitrage models will lose sense because they are not calibrated properly, right? If the calibration data is wrong, right? So please understand that arbitrage free models is when you kind of match, right? Let me write that sentence also. Arbitrage free models is, right? Okay, it's written here. Match observable market price, right? Your objective is to match observable market prices. That's the objective of your arbitrage models. But when we talk about your equilibrium models, you want to understand the economic drivers, right? Economic assumptions, inflations, consumption, etc. From the exam perspective, please understand arbitrage free models, right? You get greater price accuracy, right? You get greater price accuracy. Whether you get economic accuracy, that's not sure. To get a greater economic accuracy, right? Greater economic accuracy is your equilibrium model because it is based on your economic variables. Okay, small discussion in your book, guys. What are the types of your equilibrium model? Example here are CIR, Cox, Ingersoll and Ross model, right? This is your example of your equilibrium model, right? There are general equilibrium term structure models also. You should also understand that equilibrium model has some limitations, not given here. I think next topic also it's not touched upon, not much, but the point is that if the price are distorted, equilibrium models might hold logically well, but arbitrage free model kind of loses relevance, right? Keep that in mind, right? So I don't think there should be any problem, right? Okay, guys, fine. From the exam perspective, be ready to distinguish between the two approaches, your arbitrage free models and equilibrium models. You also please be aware that in your equilibrium model and arbitrage free model, there is a difference in calibration also. In your arbitrage free model, right, you are looking at your calibration to data. Looking at calibration to data. In your equilibrium model, right, they are not calibrated. I've gone much beyond the discussion, guys, here so that you get an idea. Even though from exam perspective, I think this will not be tested so much. Just to have a little bit of idea, know the differences between arbitrage-free model and equilibrium model. Equilibrium model is not discussed that much in your syllabus, but I've given you a greater sense that it is not calibrated, but important for your bigger economic picture. Arbitrage-free models are used for your pricing of derivatives, ensuring no arbitrage with your today's curve. Equilibrium models are more for economic interpretation, economic observations, and your relative valuation, right? Relative valuation. Makes sense? Okay. Moving on, guys. Now we'll dig deeper into Vasicek model, right? So when you talk about your Vasicek model, right? In your Vasicek model, we are focusing on mean reversion. Again, this is again important property we are talking about. One of the most exam relevant models in FRM, right? The core idea is Wasserchick assumes short-term interest rates are mean reverting. Okay, so we are adding arbitrage-free model with your mean reversion. In the long run, rates tends to gravitate or move back towards equilibrium level, right? Determined by your fundamentals, which can be your monetary supply, technology, etc. Right? There's a drift adjustment logic. If rates are above equilibrium, there's a negative drifts, obviously, to get it back. If rates are below equilibrium, there are positive drift to push the rates up. Think of it like a spring, right? Pulling rates back and forth, right? Back towards the center or up towards, from the below point. What's the formula? The dr is equal to k theta minus r dt plus sigma dw, where theta is the long run equilibrium rate, k is the speed of mean reversion, sigma dw is your random shocks, which was same as we have studied earlier. Mean reversion assumption works in normal condition but fails during your structural breaks, right? Important point for the exam perspective. You should know where the model kind of fails. When you look at the interpretation of each, right? Interpretation of each term here, please understand very, very clearly what we are trying to build here. There is a K term, which is the speed of reversion, right? Let's say you have high K. High K means the rate of adjustment back to theta is quite quick, right? When you have low k, means rates wander for longer before returning, right? Then there is gap, right? There is gap. So if there are big differences between r and theta, right, there is stronger kind of pullback, right? So that's what we have. So gap kind of matters. Okay. Then there is a drift term, which is your lambda, right? Which is interpreted as your expected rate change plus your risk premium. It was very similar to what we consider in the previous model in your when I talked about your how can we look at a lambda, right? When we incorporate higher lambda, we should not only consider it for risk premium, but we should also say that it should have incorporated expected rate change, right? And then we talk about the risk neutrality, which means that in pricing we replace your theta, which is your long run equilibrium rate, with the risk neutral kind of mean reversion level. To why do we do that? Because to ensure your arbitrage free pricing, right? To ensure arbitrage free pricing. Okay. So the model itself does one very important thing, that you're combining your arbitrage free thing with your mean reversion. Now, what are the limitations of such model? Limitation of such model is that mean reversion works well in your normal times and fails in your crisis times. So there are structural breaks like your hyperinflation, structural breaks, your regime shifts, right? Structural breaks, please understand, structural breaks are your hyperinflation. Structural breaks is not only crisis, right? It can be your regime change, regime shift. So whenever there is a structural break, this model will not work, right? The model fails. So be able to write the equation for the exam, understand what does k stands for, right? What does theta stands for, what exactly your you know r stands for, right? So be clear about that idea, right? K theta minus r dt plus your sigma dw, right? So you have a clear idea about each term, right? Theta is long run equilibrium, which is given here, right? K is your speed of change, R is your rate, obviously. Sigma dW was the previous term which you have seen. Okay. All right, guys. Now, the next part is that we are getting into non-recombining trees, right? This is a little math heavy, so please try to understand. We are getting into non-recombining tree. When I talk about non-recombining tree, what does it mean? Right? When we talk about non-recombining tree, what does it mean? Right? In this part, the objective is very clear, that we are trying to break it down further into recombining versus non-recombining. Recombining will come ahead. So when we actually build a tree using Vasicek mean reversion, here what we have taken is, we have taken the rate 6.2%, we have taken k, right, 0.03%, sigma 1.5%, theta is equal to 6%, right? So you see your theta value, right? Theta is what? Theta is your long, your, if, see, R naught was your current short rate. R naught was your current short rate. Okay. K was your speed of mean reversion. Okay. Sigma was volatility, obviously, annual volatility. Now, theta is equal to what? It's the long run equilibrium rate as given in your setup, right? Now, if I have to find, right, if you go back to, just for a second, if you go back to theta, right, you see It is long run equilibrium rate. Theta is your long run equilibrium rate. Now you look at what I'm writing. What is happening here? Please pay attention. We are trying to calculate the monthly drift, right? Monthly drift, monthly volatility, right? So if you look at the drift part, the drift part is equal to what? K theta minus R, your dt, right? K theta minus R. K was what? K was 0.03. Theta is what? Right? Theta, has it been given to you, theta? Right? If theta is given to you, how do we use it? Right? Theta, here we are using what? 18. Right? And how did we get 18? How did we reach 18 here? What has been done to get 18? Because theta is your long run equilibrium rate. Okay. And then out of 18, we are subtracting 6 minus 2%, right? And dt, right? dt is your divided by 12. Okay. That is coming to us at 0.0295. All right. And look at monthly volatility. Monthly volatility is sigma d under root dt, which is coming at 1.5% into your root of 1 by 12, right? Which is 0.43%. So here, when we are calculating your up node, right? What is happening is R naught plus your drift, right? Plus your sigma root dt, right? Which R naught is 6.2%. Drift is what? 0.0295%. Sigma dt is what? 0.43%, right? Even though the calculation is given very long here, to be fair, the monthly drift is calculated. We can, what I have done is I have calculated. This is your drift, guys. This whole part is your drift. This is your drift. This part is drift, which we have calculated already, and this part is your sigma root dt, which also, so drift we have calculated, sigma root dt we have calculated. Okay. So if we have calculated, we get your your 663%, and here it will be down node is equal to your R naught plus drift minus sigma root dt. Okay. So you have, again, this is your drift. This is your sigma dt. Only difference is the up node and down node, there is plus and minus sign. Okay. What is happening here is when you are looking at non-recombining issue, right? When you're looking at non-recombining issue, what is important to understand is that in binomial tree, we usually want your recombining paths, means going up then down is equal to going down then up. In Vasicek, your drift depends on how far the node is from theta, right? In Vasicek, your drift depends on how far the node is from theta. Okay, since that is the case, now what happens here is, so if you move up down, it is not equal to down up. If you move up down, not equal to down up, because the drift depends on how far the node is from theta, right? Meaning the tree kind of does not recombine, right? So up down is not equal to down up. Non-recombining trees due to variable size of drift based on how far the node is given from, which I told you wrote here. Starting with r is equal to 6.2, the interest rate tree of the first period is, we have built it, right? So please understand that in Vasicek model, when we have a non-recombining tree, the calculation are quite different, right? So there will be asymmetry, which we'll see here, right? And also please keep in mind how we are calculating it, right? So for all of you, please understand how the drift term was calculated, k theta minus r dt, right? Theta is your long run, your equilibrium rate. How do you calculate the long run equilibrium rate, right? How did you uh, got that thing, right? Please understand, if you have to find long run equilibrium rate, it has to be calculated separately, right? So that's what. So the first we calculate theta, and once we have calculated theta, right, then k theta minus r dt, and similarly your sigma root dt we have calculated, and then up node and down mode, and we understand that up down and down up are not equal, right? For the FRM exam focus, know the formula for node rates under your Vasicek. That's very important, right? So remember that this part, R naught plus drift sigma root dt, R naught plus drift minus sigma root dt. How do you calculate drift? How do you calculate your sigma root dt, right? Very, very important. Understand why the tree is non-recombining. That is this part, that drift depends on how far the node is from theta, right? Theta means your long run equilibrium rate, how far the node is from your long run equilibrium rate. Okay, limitations, we need to be very clear that non-recombining trees are impractical. So modifications like recombining trees, recombining approximations are later introduced, which we'll see after 2 3 slides. So uh, please be very clear that this slide kind of shows you the practical difficulty of using your Vasicek. Its economically realistic mean reversion property is good, but it makes your trees become non-recombining. And since it becomes non-recombining, it becomes your computationally ineffective, and that's what we are studying here, right? So be very clear. Like, I think if I have to highlight 3 4 things which you need to remember here, right? One is the calculation of drift. Second is the calculation of sigma root dt. Third is you should know how to calculate up node. Fourth is your down node, and fifth you should know that why we are doing non-recombining trees, right? Because drift your depends on how far the node is from your long run equilibrium rate, right? And also know how to do this calculation theta, right? Be very, very clear. Okay, moving on, guys. Next part. So now we will go more deeper. We'll try to understand it in a much better way. We are looking still at the Vasicek model, non-recombining tree. We are looking at second period illustration, right? So first we saw the first period illustration. Now I am getting into second period illustration, right? Uh, and also we'll move on to the point that these trees are kind of non-recombining, right? So if rates rise in the first period, move to the higher upper node in the period two. If the second period, rates can go up to 7.124 down to 6.258. So right, there's a calculation, but the whole point is that again we are following the same thing, right? We are now, since This is a starting point, 6.63, 5.796. This starting points will again be used. Again, we are trying to calculate drift term, right? Again, if I have to calculate, please understand, I have k theta minus r. Your that is the point we have to take, right? Theta minus r dt, right? I have, so k will be taken as your previous rate, right? This is the formula which we saw now. And if you want to go back, it was same k theta minus r dt, right? You have the same thing again. Earlier k was your when we calculated 0.03, right, which was your monthly drift, right? Kind of, sorry, not monthly drift. K was your speed of your mean reversion. K is 0.03. Here also speed of mean reversion doesn't change, right? So k is the speed of mean reversion, which stays the same, k 0.03. But your theta was what? Theta was your long run rate, right? Theta was your long run rate, which we saw here, na? Long run equilibrium rate. In the first case, the long run equilibrium rate was taken as your 18%, right? And your R was 6.2, 18 minus 6.2. What is happening here? Again, you have same thing, right? Again, you are taking 18%, right? So this also doesn't change, 18%, right? 18%. But R is changing now. Earlier it was 6.2, here it was 6.663, right? And dt is that you divide by 12, right? So that is what we have. And then your sigma root dt, I think that is part which is not changing, because we have still have 1.5%, right? And then we have multiplied by your root over 1 by 12, right? So same thing is being done, right? Only thing is that you, what is the point which you are changing in this whole calculation is that this r, you have now new value. Earlier it was 6.2, here is 6.63. And similarly here also, you see 5.796 is changing, 6.63, 6.63, 5.796, right? Rest all are same, guys, right? Up node is plus, down node is negative, up node is plus, down node is negative, right? So for different up node and down node, you see the values are not matching. There's not recombination happening, right? Because this was down node and moving up node, we are going to 6.260, right? It is not matching to your 6.258, right? And here down node is 5.394, right? So there is obviously non-recombination here that we need to keep in mind, right? See, this is a calculation which is not very difficult, but objective is that logic should be very clear, right? You go back and see the logic is k theta minus r dt. So k is same, the speed of mean reversion. Theta is long run equilibrium rate, which is same. So k and theta doesn't change. R is 6.2 here, which changes 6.2. Earlier, the next case it becomes 6.663 and 5.796, right? And then this part sigma root dt also doesn't change. 1.5% sigma and root dt is 1 by under root 12. So that part also doesn't change, right? So these two part doesn't change, but what we gather, right, from this calculation is that your Vasicek rates, right, or Vasicek tree does not recombine. From our previous step, upper node was 6.663. Now apply the same Vasicek model, which is 6.663% plus 0.03, which is speed of mean reversion k. Theta is the long run equilibrium rate minus 6.633 divided by 12 plus 1.5% by root 12. We get 7.124 in the up node, second period up node, and then we get second period down node, we get 6.258, right? Then when you have your down node, right, there also in the up part we get your 6.260 and your 5.394%, right? So calculation part, I think that is not that difficult, right? If you clearly know your drift and your this part, right? If you know the formula for drift and sigma root dt, I don't think there should be any difficult plus minus part. Why do we have non-recombining? So from upper branch, you can see I'm getting upper branch up down, we're getting 6.258. From lower branch, I'm getting 6.260. Even though they are very close, but still they are not equal, right? 6.258 and 6.260 are very close. The tiny difference means the up down is not equal to your down up. So up down is not equal to your down up, right? So this is the main property of non-recombining trees, right? So since it is not recombining, what happens is that this tiny difference makes us realize that tree fails to recombine. And as you remember, right, in the earlier models, we have said that recombining is a very good property which stops us from having infinite possibilities. Now, since recombining is not happening, so we'll have a lot of possibilities. So over many period, these differences accumulate again and again, again and again, and tree explode in sizes, becomes non-recombining. When you look at your FRM exam focus, they clearly wants you to test on this part, that why Vasicek trees are non-recombining. You should know very, very clearly, because drift depends on your current levels. Why non-recombining? Guys, please remember it, very, very important. Which I told you earlier also, right? Written in the previous slide at the same place itself. Why non-recombining? Because your, if you go back, before I write here, if you go back, I wrote the same thing there. Na? Drift depends on how far the node is from theta. Node is from your long run equilibrium rate. Another word I can write is drift depends on your current rate level. Drift depends on. Okay. Now know that this is making it computationally very, very inefficient, very, very difficult for pricing your long dated instrument. I told you, right, for long dated they will keep on adding and we can have infinite number of possibilities. So this also leaded to your later models, which is not discussed here, but your Hull White, your Black Litterman, sorry, Black Dermantoy BGT, right, adjust to your, to allow your recombining trees, right? uh, all right. So this slide kind of reinforces the practical limitation that Vasicek captures your mean reversion very, very well. We understand that, but its trees are non-recombining, which are close enough in the short, steps, small steps. But when you go for longer duration or longer steps, right, the differences will accumulate, right? So multi-period pricing will become very difficult. So that's the point. Okay. Moving on, guys. Next part is your same thing. I think the calculation is not difficult. In this slide, we will tie together what we saw in your previous two topics, right? Making the non-recombining part absolutely clear, right? So not very difficult, but just try to have an understanding. That same thing, right? The probabilities did not change. Probabilities were still same, right? But what happened was that now things are not matching. 6.258 is not matching 6.260. Right? Why? Because the non-recombining part depends on your current level, right? Current levels, right? So that is one part, means your drift depends on your how far you are from your theta, long run, your equilibrium value, right? So we are looking for a two-period interest rate tree here under Vasicek. From previous nodes, up and down path gave us 6.258, which I told you this part. From down and up path gave us 6.260. Normally in a recombining trees, up then down and down then up equals. Here we don't. This is close but not identical. Why this happens? Because your size of drift, right, which is up and down and on the right path, not equal. Why this happen? Because size of drift adjustment, your size of drift adjustment, right, depends on how far the current rate is from equilibrium rate, right? Size of drift depends on how far the current rate is from your equilibrium rate, right? After an up move, you go to 6.663. After a down move, you come to 5.796. Now, 5.796, right? Please understand, 5.796. Your this part, 5.796 is further away, right? 5.976 is further away from your theta, right, than your 6.663. Since it is further away, the down up path has a stronger pullback, right? Since further away, right, down up path has a what? Stronger pullback. Stronger pullback means stronger mean reversion than your up down path. Because we discussed initially that ultimately Vasicek model has mean reversion, it acts like a spring. So up down path. Hence, down up rate, you see, down up rate, the spring acts much more forcefully. What happens is that down up is actually greater than your up down. Right? Down up is greater than up down. Okay. All right. So I hope this makes sense. We have done the value, done the calculation. That is very, very important to understand. Understand the mechanical reason for non-recombining. The drift term depends on your theta, how farther away from you are from theta. More farther away, more it is stronger pullback for mean reversion, and that's why it is stronger jump, right? Know why this is a limitation? Because the tree grows too large, right? So when you have all these different values, tree will grow too large. And if tree will grow too large, right, you will have lot many possibilities and lot many possibilities, and they will keep on adding. It becomes very difficult in practical terms to use this kind of model in longer time horizons, right? This is a drawback of your Vasicek model, later addressed by your Hull-White and your other model, BGT models. Keep that in mind, right? So this slide is kind of hammering down or kind of hammering home that Vasicek trees are non-recombining because mean reversion strength is path dependent, right? Mean reversion strength is path dependent. Okay, moving on, guys. This was the complex part, guys. Now we are moving into the next part, recombining trees. Okay. So after studying the non-recombining trees, understanding the limitations, understanding the problem areas, why it happens, what exactly led to that kind of problem. Now we are moving into recombining trees where the model is adjusted to fix the non-recombining problem which we just saw, right? So the problem which we saw was that in Vasicek, your up-down movement was not equal to down-up, right? So we produce a two-period non-recombining trees for short-term rates. Now this made the tree non-recombining, right? We got it. So the solution here is recombining adjustment, right? Right. What is the recombining adjustment we are doing, guys? Step one is average to do middle node 6.25 at 6.260. We get 6.259 divided by 2. We get 6.259. Right. Then replace. Once you have done that 6.259, average the middle node. Right. Step two is adjust the probabilities. Replace your fixed 50-50 up down probabilities with your P1 minus P and Q1 minus Q. Right. Expected value of the rates. Right. Why are we doing it? Because the tree still matches the expected value of rate, the variance, and then solve the system of equations, right? You solve for P and Q, right? And then you try to find out the answer, right? So how do you solve for P and Q here is, if I have to find the expected value, let's say I have to find the expected value, right? What do we do here? We have to find expected value. We do what? We have P into your RUU plus 1 minus P into your 6.259%. Right? And we get 6.691%. What are we doing? Right? So see yourself, right? If you see the point here, what we are doing is that we are trying to find the expected value. So RUU and RDD are the interest rate from successive moves up, up, and down, down. So this is RUU. This is RDD. If you can't see it, I'm writing it here. RDD. So RUU, right? You multiply with the probability P. 6.259, you're multiplying with 1 minus probability P, right? Then you are getting 6.691%, right? So you are taking it back, right? You saw the same thing in FRM part 1 in when you were doing the binomial model, right? That time you did the same thing, na guys. You try to take the expected value, the probability driven expected value, right? And then for variance, again same thing. If I have to calculate the variance, that is for expected value, guys. For variance, right? Again, the formula is your, again you have to do under root, because obviously, right? If you have to calculate the standard deviance, this variance condition, right? This variance condition. If I have to find the standard deviation, right? What do we do, right? Standard deviation. We do probability into RUU, right? Minus your 6.691, which is the weighted probability we have found, right? This is taken the square, and then you take 1 minus P, same thing, you take 6.259, right? 6.259 minus your 6.691 square, right? There is a whole under root going on, guys. Okay. So the point which I'm trying to make, you can see the equation here if the formula doesn't make sense, right? So now use the standard deviation definition to form the second equation. Now, why we are equating it to what? We are equating it to our sigma root dt, right? Right, the same thing which we did earlier, sigma root dt. If you go back, the same calculation we did earlier, guys. See, sigma root dt 1.5% into multiply by 1 by root 12, right? So same thing we are doing here also. So we are equating it, this part, the variance condition, we are equating it is equal to your sigma root dt. Dt is obviously your 1 by root 12, right? So this is your second equation, guys. So there are two equations, right? One is the equation for expected values, another is equation for your variance condition, and same thing you repeat for the bottom branch also. You do the same thing for the down path, solving for your Q, right? Q and RDD. So here you're solving for RUU, and upward slope you P and RUU, and then downward you solve for RDD, right? So again, the point is that by having this kind of system, we are getting a better value. By averaging your middle nodes and adjusting probabilities, we bend the rates to recombine, which were not recombining. Trees become computationally efficient, which we want. Your size grows linearly, not exponentially. This keeps Vasicek model usable for your long dated derivative pricing. And you should understand how your recombining is forced, right? So recombining is forced by your basically three steps. One is to take the middle value, second is to replace 50-50 probability by p1 minus p, q1 minus q. Third is you take the two condition, one in the expected value condition, which is p into ruu plus 1 minus p 6.259. Similarly, q into your 6.259 into 1 minus q, your ruu into your 1 minus q, and similarly put the standard deviation definition also, right? So the combining trees is very very important because we want to have a model which does not have infinite possibilities or exponential possibilities. You simplify your computation. Arbitrage free models like your Vasicek can be implemented in your recombining trees despite there is a mean reversion, right? So again, this equation is very complex. I totally agree. So they will not tell you to calculate, but you should know, right? You should know these steps. I'm not expecting that they will tell you to solve this questions here by solving these equations. That's not part of the exam. But yes, they will expect you that you understand that what are the three steps by which non-recombination property is solved and it is converted into recombining tree, right? So first is you focus on your averaging of two nodes. Second is you remove the 50-50 probabilities by p1 minus p, q1 minus q. And third is that you use the two equations. One is your expected value equation, right? P into ruu plus 1 minus p into your 6.259. For do it for the upper node also, do it for the lower node also for the expected value, and for variance condition also you do probability into ruu minus 6.691 whole square plus 1 minus p 6.259 minus 6.691 whole square, right? Equated to your sigma root dt, right, which was your standard deviation, right? So that way we are getting the idea, right? So overall objective of this slide is to show how Vasicek moves from an inefficient non-recombining tree to a practical recombining tree that still preserves your mean reversion. Okay, keep that in mind. Moving on, guys. Next one is your Vasicek model, your rate change, your standard deviation of rate change, and half life. Very very important from the exam perspective, guys. I've seen a lot of questions coming from this part of the chapter. Basically this is most exam relevant point, right? Don't forget that, especially half life, standard deviation of rate change, etc. Now talk about expected rate change in t years. Please understand this is the weighted average of two things, right? Weighted average of your current short term rate and your long horizon value, right? So current short term rate is your R naught E minus KT, and the long horizon rate is equal to your theta 1 minus exponential minus KT, right? So remember that when you look at the interpretation, please understand as t moves to infinity, t moves to infinity, RT moves to theta, right? So what happens is that as time period moves to infinity, the RT is pulled towards the long run equilibrium, right, which is the theta value which we have known, right? If let's say today's short rate is 8 and your equilibrium theta is 6%, so you know that, right? In 5 years, so if you have been given that short rate is 8%, equilibrium is 6%, k is equal to theta, right? So in 5 year expected rate should be equal to your weighted mix of closer to 6% than 8%, right? So you move closer to your long run. You tend to move closer to your long run value, right? Factors half life. means the number of years to close half the distance between the starting rate and the mean reverting layer. This is ln2 by k. The half life tells us how long it takes us for the rate to close half the gap between your r naught and theta, right? The starting point rate is r naught, mean reverting is theta, right? It is very, if you have studied chemistry in your schools or radioactive decay, you will realize that this is a very common concept in your physics and chemistry, radioactive decay, that your half life of anything is calculated by natural log of 2 divided by k. If let's say k is equal to 0.1, right, then your half life becomes your natural log of 2, right? Example I'm taking, natural log of 2 divided by 0.1. If you solve it, it comes at your 6.93 years, right? So you can solve it, these kind of things, and come to know that how much time it takes to come back. Very important from the exam perspective, guys. Okay. A larger mean reversion adjustment parameter k will result in a shorter half life. Obviously, something which we saw in the 5.796 part also, that your there was a jump faster, right? So if, and that jump depends on k, right? If the larger mean reversion adjustment factor k, the speed of mean reversion is higher, obviously the life will be shorter, right? So the faster mean reversion, the rate forgets its starting value much more faster or much more quickly, right? Now, what is expected out of this chapter or this topic or this slide in the exam is this formula is favorite, guys. Favorite for calculation question, right? Especially they give you R naught, theta, K, etc. They tell you to find the expected rate in your T years. Very, very important from the exam perspective. Half-life concept they tested, often ask you qualitatively what happens if K increases. K increases means there is a faster pull, right? There is a faster pull, shorter half-life. Overall, keep an intuition into mind that in Vasicek, rates don't wander freely, like which happens in your model one, right, which you saw. They are anchored by your long run equilibrium value theta, right? So keep that thing in mind. So this is kind of the core for economic meaning of Vasicek, that you are tied to a long run value which is economically important or significant, right? Short rate evolves as a weighted average of today's levels, right? And again, a long run equilibrium, right? Long run horizon value. So you're, why long run? Because long run makes sense to you economically, right? Mean reversion speed k determines how fast they kind of converge. Okay, so that's what we have. And then we move into your next slide, right, which is your model effectiveness. So this uh, slide, model effectiveness. So we have seen the model effectiveness of no drift also. We have seen the model effectiveness of constant drift also. We have seen the model effectiveness of time varying drift also. Similarly, we'll see the model effectiveness of your Vasicek also. When you talk about Vasicek, right, what happens here is it ties together the strength and weakness of the Vasicek model. Okay, the key points on effectiveness which we need to keep in mind is that there are calibration and volatility structure. What do you mean by calibration and volatility structure, guys? It means that your Vasicek calibrates your R naught and theta. R naught is your starting point, theta is your long run rate to your market data, market prices, right? It produces a declining volatility term structure, right? Since you calibrate, it produces a declining volatility term structure, which you saw in one of the earlier models also, right? So, and when you produces a declining volatility term structure, it overstates your short term and understates your long term volatility. Very, very important. These are the things which are tested in the exam. They want you to ask you, right? Very, very important. This contrast with your model one, no drift, which assumed your flat volatility. So this is not flat volatility, guys. This is your kind of declining volatility term structure. Then you have the flat volatility comparison. In model one, you had flat volatility, right, which is no drift. I told you, right, which was unrealistic. In Vasicek, we have declining volatility, more realistic since long-term rates tend to be less volatile because there is less shock. We are looking at longer horizon, right? So that makes perfect sense. Declining pattern. Non-parallel yield shift is the next thing which we need to keep in mind. Vasicek produces non-parallel yield curve movement, which is very very important for us. Short-term rates react more strongly than your long-term rates. This avoids the parallel shift problem of the simpler model, right? So there was a parallel shift problem of the simpler model which we have seen, and then there is a shock dissipation because of mean reversion. Shocks fade over time as rates get kind of pulled back, right? So shocks doesn't matter much. Larger K means faster dissipation of your shocks, right? So larger reversion parameter, they dissipate faster after an unexpected inflation spike. Short rates might jump, but over time they will drift back. Equilibrium, we have seen what has happened in so inflation from 2022 to 25 now. Economic news duration is important point is that when you have smaller case, slower mean reversions, so shocks last longer, means market takes your longer to digest new information into bond prices. And then there's the parallel shift problem. Parallel shift problem is that in contrast, models without drift like your model 1 make shocks shift the entire curve equally, which is unrealistic. Vasicek kind of fixes that because here you have differential pricing or differential impact across maturities, right? So overall, Vasicek is a huge improvement over other kind of models because you're solving for parallel shift problems, you are having non-parallel shift yields, you're looking at economic new direction, you're looking at dissipation of shocks, your calibration, volatility, flat volatility comparison, right? So please remember, guys, these 5 6 points are very very important in exam. Remember the contrast between your model 1, your no drift, your constant drift, your time varying volatility with Vasicek model, right? Very very clearly. Also understand that Vasicek focuses on declining volatility, non-parallel shift, stock dissipation, right? Stock dissipation, more realistic in real world scenario. You should understand why mean reversion matters. It tempers your long-term volatility and ensures shocks don't persist forever, right? So that's the point. Overall, Vasicek is much more effective than Model 1 because it introduces mean reversion, it introduces realistic volatility, it introduces non-parallel yield shifts, right? Overall, it's a good model. It still has some calibration challenges, which is your non-recombining and recombining trees, but overall, it's a pretty good model, right? Moving on, guys. Next part is let's do practice questions. The Bureau of Labor Statistics just reported an unexpected your short-term increase in high-priced luxury automobiles, right? Unexpected short impact. What is the most likely anticipated impact on mean reverting model of interest rate, right? See, there is an unexpected short-term shock, right? And we are asked in a mean reverting model, what is the likely impact? So key concepts here are that there's a short-lived shock. Obviously, when you're mean reverting thing, the data release is not a structural shift. And it's not a long-term inflation expectation or something. It's a short-term blip. So the market expects it to fade, right? There is a high mean reversion parameter. High K means that things will move back faster. Rates don't drift away for long. And if you look at your options, right, the economic information is long lived with low mean reversion parameter. No, right? This that would apply only to structural changes, right? That doesn't apply here. The economic information is short lived with low mean reversion, right? I understand that there is short lived thing, right? But low K, right? Your low uh, K value, low speed of mean reversion will lead to low mean reversion, but that's not the case here. Then we have the economic information is long lived with a high mean reversion. Long lived is again wrong. The economic mean reversion is short lived with a high mean reversion. That makes sense when you have high K, right? High speed of mean reversion, as well as you are looking at the mean reverting model. So you know that temporary info quickly pulled back, right? So economic news duration or economic news, right, is shorter with high K. Economic, right? Economic New duration is your shorter or short-lived short-lived with high K. Okay. All right, guys. So this we have done. I don't think there should be any problem in any of these. Next one, guys. Next question is using your Vasicek model. Using your Vasicek model. Okay. You are assuming a current short rate of 6.2%. All right. Which is fine. Annual volatility of the interest rate process of 2.5%. Long run mean reverting level of 14.2, right? So theta is 14.2. Okay. And speed of your adjustment k is equal to zero point 0.4. K is equal to zero point 0.4. Okay. Horizon is 1 month, means dt is equal to 1 by 12. Okay. So we need to find the upper and the lower nodes after 1 month, right? So I don't think there should be any problem because if you know the formula, dr is equal to, we calculated in the theory part also, right? Kr is equal to theta minus r dt plus sigma root dt, right? So very simple. If you calculate the first part, your k theta minus r, that you put the values for k theta minus r dt, and you put the values, k is your 0.4, theta is your 14.2%, r is your 6.2%, dt was 12. You solve it, you get 0.27%, right? And so drift is your, this part is 0.27%. Then volatility is your sigma root dt. You calculate it, right? Sigma is given to you 2.5%. Root dt is your 1 by root 12, right? You solve it, you get your plus minus your 0.72%. This is volatility adjustment, guys, right? You get 0.72. I'm just saying plus minus because you have to do plus minus, nah? So that's because you have to do upper and lower node, right? Plus minus 0.72, right? So you put in the values, you get 7.16, one value. Other value, you get your your what you say, 5.71. How do you get these values? If you want, I can write it here also above. What you get, you already know that the previous value was what? The previous value was 6.2. Now you had 6.2. In that, you added your drift term, which was your 0.27, which made it 6.47. That you added your 0.72, right? You got your 7.16. And then 6.2 was the original value. There you added the drift term, that's fine. But you have to subtract 0.72, right? So this is what you have, and you get 5.71. Don't subtract the drift term, guys. Only subtract the volatility component, right? Volatility adjustment. So not difficult at all, guys. Very straightforward. Right answer is your D option. 5 point. And this is the option we have. Very straightforward. Very easy question. Okay. Next one, guys. Next is John Jones FRM. Right. John Jones FRM is discussing the appropriate use of mean reverting models relative to no drift models, models that incorporate your drift and holy models. So all models they are discussing, and he makes the following statement, right? So when you're discussing all kind of models, let's evaluate each statement. Uh, it's saying that statement one, both model one, which has no drift, and the Vasicek model assume parallel shift from changes in the short term rate, right? Now, I don't think that's true because Vasicek model, model one does assume your parallel shift, all maturity move equally, but Vasicek model allows your non-parallel yield shift because mean reversion impacts your short-term rates more than your long-term, right? So this is not correct, right? Next one is the Vasicek model assumes decreasing volatility. I told you in property, that's correct, right? While model one assumes constant volatility of your short rate, right? So this is perfectly correct. Third is, yeah, the constant drift model, model two, is more flexible model than Holy model. No, right? Model two is not flexible, right? Holy model is more flexible, right? So Holy model is more general because you are incorporating your time dependent volatility, right? Time varying volatility, it drifts over time. Lambda t dt we have, so this is wrong, right? How many of these statements are correct? One statement is correct. Only statement two is correct. So one statement is correct, right? So very straightforward. If you know the property, you're able to do it. All right, guys, with this we have finished this chapter, right? Quite a tricky chapter, not easy to understand, right? But what is important for every one of you to realize is that we are doing a very complex chapter where we are trying to understand two different kind of modules, right? One was focusing on your term structure models, one was focusing on your arbitrage free models. So we started with, like, if you have to recap the whole thing, we started with model one where we assumed no drift, right? Then we looked at that effectiveness. Then we moved to constant drift, looked at that effectiveness. Then moved to time varying volatility Holy model. That we looked at that effectiveness, and then we moved to your difference between arbitrage and equilibrium model. Then we looked at your Vasicek model, right? Vasicek model, especially the non-recombining part. Then we saw how non-recombining part is problem and how that can be resolved. Then there are three steps by which it can be resolved. One was you're taking the mean value. Second was taking the probability p1 minus p, q1 minus q, and then you taking the two equation, which is the expected value and the standard deviation property value, right? We solve for those equations, and then we move it to your understanding more of the properties of the Vasicek model, finally recombining trees, etc. And then we kind of wrap it up by the advantages of the Vasicek and the comparison. Okay, so go back, understand it, try to analyze it properly, have a holistic understanding. Again, my point here is that you have to look at more conceptual knowledge than your heavy math language, right? Focus more on better conceptual understanding than heavier math understanding. If you have a better conceptual understanding, you will be able to solve. Little bit of math is there in between that you have to see. Like, otherwise, learn the formulas of the model, guys. Have a very clear idea about models, mean reversion, speed of mean reversion, half lives, right? Standard deviation, standard rates, right? Have that clear cut idea. So formulas, if you have that, I think you're perfectly fine, right? Overall, this is a very complex chapter where you have to have a very clear idea about that there are two parts to the model. One is the deterministic, one is your stochastic. And when you are trying to model it, right, the deterministic part, you have to understand that sometimes drift is not there, deterministic part is not there. You only have to consider stochastic part. Then how do you do, which no drift you start, and you move to constant drift, and you move to your time varying drift, and then you move to your uh, incorporation of drift also, right? So go back, revise it, guys. I hope you like this video, and then we'll meet again in the next chapter and discuss more. Okay. All right, guys. Thank you.